This is the last part of the lectures on the moon. The first thing that we're going to talk about is whether there is a dark side to the moon. What I mean by that is a side that is always dark. So here we have a moon that is not rotating. That is to say that there is always one face here with a blue crater which is lit up by the sun, and there's one here with a red crater which is mysteriously glowing so we can see it, which is never lit up by the sun. And we're going to see what happens if this does not rotate. So here we have that once it gets to this first quarter, half full phase, now we can see the blue crater still, and now we can see this red crater. Sorry, we can see the blue crater, whereas we couldn't before. We can still see the red crater. As it moves on, it's going to get to the point where we can only see the blue crater and not the red crater. As it moves around to third quarter, now we can see both craters again. And as it moves back, we're back to seeing the red crater only. So this would be that we could see this side would be dark, but we would see both sides. And that's not true. As the moon moves around the Earth, we don't see both sides. We only see one side. And that is because of what is called synchronous rotation. So here we have that the same side of the moon is always facing towards us. So it's always got the red crater facing towards us. And in order for this to happen, it has to be that the moon rotates with a period that is exactly the same as the time it takes to go around. So this has gone all the way around from this side to this side to this side to this side and back again in the time it took to go all the way around. And this is called synchronous because the rotation and revolution periods are synchronized. Now, what is it that causes that? So here I have a slightly unrealistic setup of 3 billiard balls that are under the, very large billiard balls in fact, that are under the influence of a planet that looks remarkably like ours. And they're being pulled by the Earth. And so here they're lined up in a line radially away from the Earth. So the one yellow ball is further away than the 2 green ball, which is further away than the 3 red ball. And so as they're being pulled, this one feels more force, this one feels a little less than 3, and this feels less than both. And so as they are accelerated, the force that they're feeling, they're all identical masses, this one's going to accelerate the most, and this one's going to accelerate the least. So let's see what happens. So we have a situation where this one has moved the most, this one moved not quite as far, and this one's moved the least. There we go. But what does this look like if you stood on ball number 2? From the point of view of ball number 2, we find that 1 moved away from the Earth and 3 moved towards the Earth. So from the perspective of somebody observing from here, gravity was pushing the ball away, not pulling it towards the planet. Now that's really important for understanding tidal forces. So here we have the same situation. We have the moon. The moon is pulling on the Earth. The Earth is being pulled towards the moon. This side of the Earth is being pulled more. The middle part of the Earth is being pulled a little less. And the far side is being pulled even less still. Okay, so if you stood on the Earth, which most of us are, what does it look like? Well, the middle part is not being pulled at all. The side that's being closest to the moon is being pulled towards the moon, and the side furthest away is being pushed away. Same idea as the billiard balls. And this is what gives rise to tides. And so what you get is that the Earth does react to this, but part of the surface of the Earth is fluid, can really flow as a result of the force due to the gravity from the moon. And so what you get here we've got the moon here is somewhere over here. And so you're going to have some of the ocean is going to be pulled towards the moon. The Earth is also pulled towards the moon, and the ocean on this side is pulled not as much as the Earth on this side. So you get, effectively, a bowing out there and a bowing out there. And so if you're stood at this point, you'll get a high tide. As the Earth turns and you get to here, you now have a low tide 6 hours later. You now have a high tide 6 hours later. You now have a low tide. Now this is ignoring the fact that the moon is going around the Earth. So over the course of a day, it's moved through a certain angle, and so it doesn't take quite 24 hours to get back to the same point. Now, consider what happens when the moon and the sun are lined up. So in this case, the moon is over here, the sun is over here. That is a full moon. Or you could have the moon on this side. It could be a new moon. You're going to get more pull in this direction, because the sun is also pulling more on one side and less on the other, and so you get the same effect. And we call this a spring tide. And basically, the difference between this tide and this high tide and this low tide, is huge. This is much more bowed out here, but that means you've got less here because you've got a finite amount of water. Whereas if the moon is in this direction, or in fact down this direction, and the sun is over here, now you've still got the same amount of water, but the sun is pulling the water this way a bit, and the moon is pulling the water this way a bit. And so what you get is the difference between the low tide and the high tide is much smaller. So when you have a full moon or a new moon, you get bigger differences between low tide and high tide. When you have a quarter phase moon, you have much smaller differences between low tide and high tide. And these are called spring tide and neap tide. And here we have another representation of that. So here's the sun, here's new moon, here's full moon, and you get low tide and high tide, but this is pulled out much more. You can see here the difference between low tide and high tide is much less, and that's because the moon is in this direction and the sun is in this direction. Actually, it's more complicated than that. So here we have a situation where this is on the winter solstice. So the sun is above the Tropic of Capricorn, and so it is directly over here. And here we have, this would be an eclipse, in fact, because we have a new moon. And they're both pulling in this direction, so you get this bulge here, but the spin axis of the Earth is offset from that. And then sometimes the moon will be up here or down here, and so on. But let's just consider this situation. We've got the bulge this way, but we're spinning around this axis through the poles, and so the person in Canada or Alaska or somewhere up there is going to see a lower tide at this point and a higher tide at this point. So you'll have a big high tide and a small low tide, and likewise in the in-betweens. And so it gets more complicated. This also only accounts for the effect. It basically assumes you've got a fluid over a perfectly smooth sphere, and that's not true. We've got land masses, we've got different depths. So once you account for turbulence and friction, you get some really interesting effects. So for instance, the Gulf of Mexico doesn't have 2 high tides and 2 low tides a day. It only has 1, and that has to do with the reaction with the turbulence in the water. Now, I mentioned friction. So basically we've got the ocean is moving relative to the seafloor. So you have the ocean is being pulled towards the moon, but the seafloor is moving. And if you've got friction, then you have heat. And the heat is dissipating the Earth's energy. So you're actually using some of the Earth's energy. So the Earth has to slow down. And in fact, it slows down by about 2 milliseconds a century. So it's not something that we need to worry about every day. But over the course of millennia, it makes an effect. So the length of a day increases. And so we have a geologic record that shows us how long a day is. And then this actually comes from the fact that we know how long a year is from different cycles that happen in soils and in plants, and then they're laid down, and we can work out how many days there are in a year. And it turns out that there were 397 days back 10 million years ago, and 10 million years is not that long ago. And so we also get tidal motion in solid bodies. It's just not so evident. So the Earth is causing friction on the moon. It's just that you don't see it quite so much, and the reaction is not quite so much. But that means that you have the same thing. You have rocks being pulled towards the Earth and pushed away from the Earth, and as the moon spins, it's going to have a friction effect, and you're going to lose energy, and the moon's rotation is going to slow down. And that's what gives rise to synchronous rotation. So basically, once you get to the point where the rotation period is the same as the revolution period, it can't slow down anymore. Why is that? Well, once it's at that point, the side that's pointing towards the Earth is always pointing towards the Earth, and the side that's pointing away from the Earth is always pointing away from the Earth. So you no longer have this friction. You no longer have the rubbing together of the rocks as the moon spins. And so this is why this sort of synchronous rotation is normal. And in fact, this is something that will happen not just with the Moon and the Earth, but it's already happened to Pluto and its moon Charon. It's already happened to several of the moons of Jupiter and Saturn, and it probably happens to binary stars as well. And so here I have an animation, and this is going to show you Pluto and Charon. And so here we have them going around each other, and you can see that not only is Charon always keeping the same face towards Pluto, but Pluto is always keeping the same face towards Charon. So they are both synchronized. And that's really important. So what are the consequences of tides? Well, we can basically assume that the Earth-Moon system is a closed system, and so angular momentum is conserved. And so what happens if the Earth slows down? It's slowing down because it's dissipating energy, and that means that the Moon has to move further away to conserve energy. Remember that you have MVR, so if you move away, you can slow down. But what does that mean? That means that as the Moon moves away, its orbital period increases. And so as the Earth slows down, the Moon moves away, and its orbital period increases. So both the Earth is slowing down, and the Moon is getting to move through a longer month. And so a day gets longer, and so does a month. Now, this is going to happen to the Earth. We saw this in the animation of Charon and Pluto. The Earth is slowing down, and eventually the same bit of the Earth is going to be facing the Moon, and then it won't have any more friction, and so it'll just be stuck like that. And so the Moon will be in a geosynchronous orbit, which is kind of interesting. It means that the Moon will be over one spot. You'll have to travel to the other side of the Earth to see the Moon if you're born on the wrong side. But it's going to take 10 billion years, and since the Earth will be swallowed by the Sun in less time than that, it's really academic. But you get the idea, and you can see how, depending on the system, you can have this happen faster, which is what has happened for some binary systems and for systems like Pluto and Charon, systems like the moons around Jupiter. And at that point, because the Earth is slowing down and the Moon is moving away and its period is going down and its rotation is going down, then an Earth day will be the same as a month, and both will be 50 of our current days. Okay, so that's an idea of how it's going to evolve, but it means that our days are getting longer. So as it is, they're already longer than they were in the past. Even if we go back to the time of dinosaurs, it was, 20-some hours long, but not 24. And we'll also get to a point where, because the Moon is moving away, the effect of it on our tides is getting less and less, and eventually there won't be tides. In the past we had shorter days, and the tides were more violent. That is, the difference between high tide and low tide were much bigger because the Moon was closer to us, so the effective difference between high tide and low tide were bigger. And so what we have is that we will also not have eclipses, or at least we'll only have annular eclipses, and the annulus will get fatter and fatter. That is to say, less and less of the Sun will be blocked, because the Moon is going to get smaller and smaller as it moves away. Okay, and that brings us to a couple of other interesting ideas. One is this idea that's called libration. So here here's the Earth, and here's the Moon. And it takes the Moon 27.3 days to go around the Earth. It also takes 27.3 days to spin on its axis. But when it's at this point, which is perigee, you can see that it's spinning at a speed that's not quite fast enough. And so actually at this point it's not spinning fast enough, and so compared to the rate at which it's going around. So it's going around here and it's not spinning fast enough, and so we actually see just a little bit of this side because it's not spinning fast enough to stay quite lined up. But as it moves around, it's going to be slowing down until eventually you get to basically the average speed, and the average speed that it's going at is the same, is relevant for having it spin so that it's pointing the right way. And so now you have that the face that goes towards the Sun is kind of the face that we think of. But then as it goes round to apogee, it's now moving faster in its spin than its orbit. So now we're going to see just a little bit more of this side and a little bit less of this side because it's spinning too fast compared to the speed at which it's moving. And so we actually see very slightly more than just one face. Now I'm going to show this, and this is going to show how we see a little bit more on this side at one end of the orbit, a little bit more on this side at the other end. But also, the moon is moving through an orbit that is inclined at 5 degrees. So sometimes when the full moon is at that point above the Earth, we see more of the underside, and sometimes when it's at the point below the Earth, we're seeing a little more of the top side. And so we get what seems to be a bit of a wobble. So this is going to show you, so that was all waning, and now it's waxing again, and now it's going back to waning. And I'll show it again, and you'll see as it goes through here, it's wobbling so that we're seeing a little bit more of the top, and then it goes back seeing a little bit more of the bottom, and we're seeing a little bit more of one side and a little bit more of the other. And this is what we need. This is what we get because the orbit is both inclined to the ecliptic and because the orbit is elliptical.